Okay, so we're coming up on our last couple of sections here. So I just want to come on and remind you first that make sure you are looking at your homework assignments. Use those as study materials in addition to any exam reviews and things like that. Don't consider an exam review to encompass 100% of everything we might see. So use all your resources to your advantage. Look at those checks for understanding. Uh, Quizzes, so forth. There's plenty of feedback available to you. Make sure you're looking through everything. Okay, don't hesitate to look through the textbook. That's also a valuable resource as well. So again, if you need anything as far as preparation, things like that, please contact me. Let me know. Be happy to email you back or get with you about what I can do to help you prepare as we approach that final bit of the semester. Okay. So again, just be in touch if there's some way I can help. All right, so I'm going to switch over to the document camera here. We're going to talk about section 6.3, which is about orthogonal projections. Okay, so to get an idea of where we're headed here with orthogonal projections, okay, I'm going to have an orthogonal basis, okay, similar to what we've talked about in the last couple of sections. And this orthogonal basis is going to include 5 vectors u1 through u5. Okay, and each u sub I is in R5. So this is actually a basis for all of R5 because I have 5 vectors in a basis. U5 is 5-dimensional, so it has to span the same space. Okay. Okay, so I have that orthogonal basis. Then we know that I could write any vector in R5 as a linear combination of those vectors. So C1, U1, C2, U2, C3, U3, C4, U4, and C5, U5. And we could do that for any vector in Y. Okay, so that's for any Y that's in R5. Okay, because I know it has to span the whole space. So if I pick out one of them, it clearly has to span R5. Okay. Well, maybe I want to come up with a vector that relates to Y that's just in the space W, and W is the span of U1 and U2. Okay, so W is a subset here. It's a subspace of my orthogonal basis. It's a subset of my orthogonal basis, but it's a subspace within R5. Okay, and we're trying to figure out what a vector Y would be that's in that span. Okay, well, I know these are orthogonal, okay, because all of U1 through U5 have to be orthogonal to each other. So U1 and U2 are clearly orthogonal because they're in that basis. Okay. I also know then if I take a vector C1, U1, C2, U2, this vector, I can use orthogonal projections to find how it relates to Y. So I'm actually going to find a Y hat that's going to be equal to C1, U1, and C2, U2. But we learned last section that I can do this C1 and C2. We actually learned in section 1, and in section 2, we talked about calling it a projection. I can call this Y hat the projection, okay, of Y onto the space W. Now I said we could use the W or the U1, U2 interchangeably, but now I have 2 vectors spanning my space and not just one. So what we should notice here is I can take my Y hat, okay, and C1 and U1 is exactly what we did, C1 and C2, I mean, is exactly what we did for the projection, okay? We're going to take U1.Y and we're going to divide that by U1.U1. And then we're going to multiply it by U1. And the same thing for C2. That's going to be U2.Y over U2.U2, or the norm squared. And we're going to multiply that by U2. Okay, so I can break down this projection into 2 smaller projections of Y onto U1 and another one that is Y onto U2. Okay, and remember this projection Y bar, so I can take any vector Y and write it as Y hat plus some vector Z. Okay, and remember then that Z is orthogonal to Y hat, and it is so since it's orthogonal to y hat we know is in W. So if it's orthogonal to y hat, then Z is orthogonal to all of W. So it's orthogonal to y hat, thus all of W, which means Z is an element of W perp. Okay, so Z is perpendicular. Now, also as I look at this, I have 3 more vectors. So Z is actually in the span of those remaining 3 vectors because it's got to be perpendicular. This is U3, U4, and U5. Because it's got to be perpendicular to U1 and U2, and it's got to be in R5. So it's that those remaining dimensions that we didn't cover with U1 and U2. It's got to be in those other dimensions for U3, U4, and U5. Okay? So we go through all of this in order to say we have a theorem 8 here in section 6.3 called the orthogonal decomposition theorem. Theorem 8, orthogonal decomposition theorem. Okay? Orthogonal decomposition theorem. Okay? And so what that orthogonal decomposition says is just an encapsulation of what we have talked about to this point. Okay? So as I look at this, I'm going to have W is a subspace of Rn. Okay? Then each Y that's in W can be written as Y is equal to Y hat plus Z, with Y hat in W and Z in W perp. Okay? Which means given an orthogonal basis which is U1 through some UP for W. So I have an orthogonal basis now for all of W. So it was U1, U2 in the lead-up example we talked about. Okay. Then, not they, Y hat is equal to the projection of Y onto W, which is equal to the different components, Y dot U1 over U1 dot U1 times U1 plus Y dot U2 over U2 dot U2 times U2 plus, and that goes all the way out, Y dot UP over UP dot UP. Okay, so I can break down this Y hat, this Y, into a projection, and that projection I can simply take the components of each one. So each one of these is a projection of Y onto U1, Y onto U2, Y onto U3, 4, 5, all the way out to UP. And I can simply add those projections together, and that will give me my Y hat, or my projection onto the whole space Y, whole space W. And Z, remember, is going to be Y minus Y hat. Okay, so once you find Y hat, you simply find Z by subtraction. Okay, that's our orthogonal decomposition theorem. Okay, so let's look at a first example here. Okay, I'm going to go to the next page just to make sure I don't run out of room. Okay, so I'm going to have a vector Y. My vector Y is going to equal to -1, 4, 3. And my vector U1 is going to be 1, 1, 0. And my vector U2 is going to be -1, 1, 0. Okay. So let's take a look at those vectors U1 and U2. Okay, if I do U1 dot U2, I do 1 times -1 is -1. plus 1 plus 0, I get 0. Okay, so U1 and U2 are clearly orthogonal. Okay, so W is going to be the span of U1 and U2. We know U1 and U2 are orthogonal, which means they're linearly independent. So U1 and U2, the span of that will be a basis. So U1, U2 is a basis. Okay. And I want to find two vectors. Okay. The first vector is going to be y hat. So I want to find a vector. Make sure I say the right words here. So we're going to find the projection. Okay. We're going to find a vector that's in W and a vector that's orthogonal to W. Okay. So I'm going to write y as the sum of two vectors okay, we're going to have y hat that's in W and z that is orthogonal to W, which means it's in W perp. Okay, that just means orthogonal to W. Okay, and we do that with the orthogonal projection. Okay, so what I'm going to find first is I'm going to find y hat, which is the projection onto W for y. Okay, and to find that, I'm going to do the projection of y onto U1 plus the projection of y onto U2. Okay, again, I'm writing out all the steps here because I want to make sure we understand where the things are coming from. So I'm going to do y dot U1 over U1 dot U1 times the vector U1, y dot U2 over U2 dot U2 times the vector U2. Okay, continuing on, y dot U1, I've got -1 and 4 and 0, so I get 3. Okay, U1 dot U1 is 1, 1, and 0, so that's 3 halves. Okay, U1, so by vector U1 is going to be 1, 1, 0. Okay, y dot U2, that's going to be -1, and that's going to be -1 times -1 is a +1. 4 times 1 is 5. U2 dot U2 is going to be 1, 1, and 0. Okay, so I got 5 halves. Okay, just to reinforce what we had there, right? I had y dot U1, that was -1 plus 4, that was 3. U1 dot U1, that was 1 plus 1, that was 2. Y dot U2, that was 1 plus 4, which is 5. And U2 dot U2 is 1 plus 1, that was 2. Okay, and then my vector U2 is -1, 1, and 0. Okay, so we continue on now. We're going to have 3 halves, and 0. Again, multiplying the 3 halves at constant, scalar. -5 halves, and 0. And we're going to add those. So 3 halves plus -5 halves is -1. 3 halves plus 5 halves is 8 halves, which is 4. And 0 plus 0 is 0. So my vector y hat is -1, 4, and 0. And notice that this is in W because it is a linear combination of U1 and U2. So now to find Z that's in W perp, I simply do y minus y hat. Okay, y, remember, was -1, 4, 3. And y hat is -1, 4, 0. Okay, so I have -1 plus 1, so I get 0. I have 4 minus 4, I get 0. And 3 minus 0 is 3. Okay, and so you can imagine then if I take y hat, and z that I just found is equal to z. Let me make that equal to z just so it's clear. All right, that's equal to z. If you do y hat and z, you do the dot product, you get 0, 0, and 0. Add those together, you get 0. So those are clearly orthogonal. Okay, and if you look back at U1 and U2 had zeros in that third position. So it makes sense then that Z, which is not in the span of U1 and U2, would have only a position in that third spot. Okay, that's a logical result there. Okay. All right, so another way we could word this question, okay, is I'm going to have this type of question, I should say, not this question. I'm going to have U1, U2, U3, and U4 an orthogonal basis for R4. Okay, so orthogonal basis for R4. We're going to write X as the sum of two vectors one that's in the span of U1, U2, and U3, and the other that's in the span of U4. So I've split my space that has U1 through U4 into two separate subspaces, one that's U1, U2, U3, and one that's U4. And I want to get two vectors that when I add them together, I get my new vector y, or my previous vector x. Okay, so I called it x this time. So let's write down what these vectors are and then figure out how we're going to go about this task. So U1 is going to be 0, 1, -4, -1. U2, 3, 5, 1, 1. U3, 1, 0, 1, -4. U4, 5, -3, -1, and 1. Okay. My vector x that I'm interested in decomposing, notice that word there, so it hints at what theorem we're going to use. Use the decomposition theorem. My vector x is going to be 10, -8, 2, and 0. Okay, so I want to take x and turn it into two vectors, which I'll call y1 and y2 for now. Okay, so y1 is going to be in the span of the first three basis vectors, and y2 is going to be in the span of the fourth basis vector. Okay, now the easiest way to come up with a vector that's in the span is to use the orthogonal projection. So I'm going to find one of these vectors using an orthogonal projection. Now I have my choice. I can do either one. I can either do an orthogonal projection onto the first space here, or I could do an orthogonal projection onto the second space, U4. Okay, so I have my choice. Now as I look at that, would I rather do 3 computations to find the orthogonal projection on the first space and add them together, or I could just do 1 computation for the second space. Okay, so I'm just going to do the 1 computation. So what we're going to do then is x is going to be equal to the projection of x onto U4, because it's the alone in its space, plus some vector z, right? We might call this y hat. So instead of calling this z, we're going to call this y1. So that's going to be my y2. So the projection of U4 onto x onto U4 is going to be x dot U4 over U4 dot U4 times U4. So x dot U4, that's going to be 50 minus 24, so plus 24, so 74, plus 2 is 76, and 0, so I get 76 for the numerator. Then U4 dot U4 is 25, plus 9 is 34, plus 1 is 35, plus 1 is 36. So 76 over 36. And that's going to be times U4, which is 5, -3, -1, and 1. Okay, so I've got a fractional situation here, but I can reduce or simplify 76 over 36. Hey, use your calculator, whatever works best for you. I get 19 over 9. Okay, times my vector u4. So x is equal to, this is going to be 19 over 9 times 5. So 19 over 9 times 5. Okay, 19 times 5 gets us 95. So I've got 95 over 9 for the first coordinate. 19 over 9 times negative 3. So I'm going to have negative 57 over 9. Negative 1 times that, so negative 19 over 9. And then 1 times that, so a positive 19 over 9. And now I'm subtracting from 10. Okay, because I'm doing x minus this x hat, or this projection that I just found. Okay, so if I do 10 minus 95 over 9, okay, I get negative 5 over 9. That would be 90 over 9, so subtracting. Negative 8, and again, I'm subtracting now 57 over 9. So that gives me a negative 43 over 9. Okay, 19 over 9 plus 2 minus 19 over 9. So I'm going to have 18 and 19 go together to make 37 over 9. And then 0 and 19 over 9 will, of course, just make 19 over 9. But negative, because I need them to add up together. Okay, and so there's my two vectors. There's my decomposition. Okay, so to decompose this vector, what we have to do is we simply take a projection onto one of the spaces, and then the other side will just be, we get there by subtraction. Okay, and so you can do a projection onto either space, but it makes the most sense to do the easier one. So if I only have one vector in one of the spaces, then that is a much easier projection, as opposed to having to do it 3 times and then add the results together. Okay, so to give you an idea of what we are looking at here, I'm going to borrow the textbook's picture because they do a good job on the picture, so I'm just going to steal it. Okay, so this projection, right, I have a vector y that you see here represented. So imagine it extends out from the origin up to that vector y. And you see this orthogonal projection is sending it into the plane between u1 and u2. Right, you can see that right angle that's formed along all 3 of these, right, in this triangular prism shape. Okay, so that's what an orthogonal projection is doing. It's taking that vector and sending it down to its orthogonal, to the place that is the right angle. And we also know from geometry that that's going to be the shortest distance down to that plane. Okay, want to take the shortest distance, that's going to give me a right angle, and you see that is going to be made up again of those different orthogonal projections. So it's the projection onto this line, the projection onto this line, and we put them together, we get the projection into the plane. So that's the geometric picture that applies here. Okay. All right, so we have another theorem in this section. It's theorem 9. It's the best approximation theorem. Best approximation. Okay, which says largely what that picture showed that I told you, right? So if you've got a subspace and so forth, y hat is the orthogonal projection of y onto the subspace W, where W is a subspace of Rn. Okay. Y hat is the closest point in W to y, okay, to the vector that's being projected, okay? Another property is that if y is actually in the space that we are looking at, so if y is in W, which is equal to the span of U1 through UP, then the orthogonal projection of y of, I got my symbols backwards there. The orthogonal projection of y onto w is actually just y itself. Okay, because it's already in the space. So when you project it into the space, it doesn't go anywhere. Okay, it's still going to be in that space. So it didn't move. And it's got to be the closest point. So it wouldn't be anything other than just y. Okay. Okay, so let's do one more example here. So in this example, okay, W is equal to the span of U1, U2, and U3. And we want to write y as the sum of a vector in W and a vector orthogonal to W. Okay. So my vector y is going to be 4, 3, 3, negative 1. A vector u1 is going to be 1, 1, 0, 1. So that'll be pretty easy to work with. My vector u2, negative 1, 3, 1, 2. And my vector u3, negative 1, 0, 1, 1. Okay, so I want to get a vector that's in W and a vector that's orthogonal to W. So what I want to do is I want to do an orthogonal projection. So I'm going to have y hat plus z. So y hat and z are the two vectors I'm looking for. Y hat is going to be the projection of y onto W. And then, of course, z is just going to be the difference. Okay, so y hat, I'm going to need the projection of y onto W. So I'm going to do y with u1 over u1 dot u1 times u1. Same thing for u2. Y dot u2, u2 dot u2 times u2, and y dot u3, u3 dot u3 times u3. Okay. So y dot u1, that's 4, and 3 makes 7. 0 and 1, so I'm up to 8. U1 dot U1 is 1, 1, 0, and 1, so 8 thirds times U1. Y dot U2, that's negative 4. 9 makes 5. 3 makes 8. Minus 2 makes 6. U2 dot U2 is going to be 1 and 9 makes 10. And 1 and 4 makes 15. Times U2, and y dot U3 is going to be negative 4, 0, 3 makes negative 1, negative 1 and negative 1 makes a negative 2, and then U3 dot U3, I'm going to have 1, 0, 1, and 1, so I get 3. Okay, so my vectors then, 8 thirds times U1, so 8 thirds, 0, 8 thirds. 2 fifths times U2, so negative 2 fifths, 6 fifths, 3 times 2 fifths, 1 times 2 fifths, and 2 times 2 fifths is going to be 4 fifths. Okay. U3 then, I've got negative 2 thirds, so I've got positive 2 thirds when I multiply, 0, 2 thirds, and 2 thirds. Okay, and we got to add those together. So 8 thirds and 2 thirds is going to be 10 thirds minus 2 fifths. Okay, that is 44 over 15. I got 44 over 15. Okay. Next one, I've got 8/3 and 6/5. Okay, you'll get some ugly fractions. It happens. Okay, so I've got 58 over 15. 2/5 and 2/3. That's 16 over 15. Okay, and then I've got 10/3 and 4/5. 10/3 and 4/5 is going to come out to 62 over 15. Okay, so there's my first vector. Now my second vector, I need to subtract. Okay, so I'm going to take my y and subtract it from what I found here. Okay, so I'm doing y minus y hat. So 4 minus 44 over 15. So 4 is 60 over 15. So I get 16 over 15. Okay. Next coordinate in y is 3, which would be 45 over 15. Okay, so I get negative 13 over 15. 45 minus 58. Third one then, I've got 3, and I have 16 over 15. So 45 minus 16 is going to be 29 over 15. And then the last one is negative 1, so that's negative 15 over 15. So 15 minus 60, negative 15 minus 62 is going to be negative 77 over 15. There's my second vector. So I've got y and I've got z. Okay, so I can decompose those vectors accordingly. Okay, don't be alarmed by some ugly fractions. It happens because you have a lot of division, a lot of different dot products in this process. Okay. Okay, so if a question tells you to find the closest point, you're simply being asked to do the orthogonal projection. Okay, I'm not going to do a separate example because it's the same process of the orthogonal projection. It's just another way of wording the question. Find the closest point. Okay. So the general idea here, right, is that you are projecting and subtracting, projecting and subtracting. Okay. All right, so one more theorem and just a couple more properties to enforce here. So theorem 10. Theorem 10 says I have an orthonormal basis for W, and it's inside of Rn. Then I know that the projection of W, y onto W, is equal to y dot U1 times U1 plus y dot U2 times U2, and so forth, all the way out to y dot UN. Now, you might be thinking, wait, we left off part of the projection. But notice this is an orthonormal basis now, not an orthogonal basis. So remember, in an orthonormal basis, the dot product of a vector in the basis with itself is equal to 1. That's what it means to be a normal vector. So the denominators of all these fractions were 1. So we just simply didn't write them. Okay? So if I have a matrix U, and the matrix U has all of the vectors that are in this basis, U1 through UP. Okay? Then what I'm doing is that the projection of y onto W is actually just equal to U times its transpose times the vector y. Okay? Because U times its transpose is going to wind up having me do all these dot products. Remember in 6.1 I said the dot product is just a multiplication of a vector times a transpose of a vector, so that you get a column and a row. So that's all we're doing here. I'm going to have columns and rows when I do U times its transpose. Okay, and this works for any y in Rn. Okay, So it's just a consequence then of if it's orthonormal, we kill off all these denominators, okay? So that makes the process a lot easier because all your divisions are by 1, okay? So keep that in your mind, okay? So what we have then, right, is that if it's orthogonal to, if it's a projection into a space, then it's orthogonal to the other parts of that space, right? So if I have a subset, right, say I have Rn, and it's broken down into W and V, so 2 different vector spaces, okay? I can do the projection of a vector Y onto W, and it will be added to something that will be a vector V, okay? So I'm going to have Y as can be broken down into those 2 pieces, okay? My vector V has to be inside of V, and my vector V is also in W perp, okay? So this would be Y hat, that's an element of W, and V would be an element of V, but V is also an element of W perp, okay? So you can always decompose a vector into something that's in a space and something that's orthogonal to that space or orthogonal to those vectors, okay? So the big thing here, right, is you're looking at projection, okay, which remember is that's the projection of Y onto a vector. You're going to do Y dot U1 over U1 dot U1, okay? And if you're going on to a full space with multiple vectors, then you can simply do the component projections and add them together, okay? And if you need Z that's an element of W perp, then you find Z by simply subtracting the Y hat, which would also be, Y hat, remember, is defined as the projection onto the space W, okay? All right, so that covers all our properties for orthogonal projections. So our last section is going to be 6.4, which is the Gram-Schmidt orthogonalization process, which I know is a mouthful. Okay, that's GSOP for short. Okay, where we're going to take a set of vectors and find a corresponding set that is an orthogonal set, because orthogonal sets are easy to work with. We know the dot products between them are 0. We know if we can do orthonormal, we know the dot product of itself is 1, so we can do that even better. We also already know how to take an orthogonal set and make it orthonormal. You just divide by the norm. So we want a process then where I can get orthogonal vectors or orthonormal vectors that will be the same space as the one we're interested in. Because if I can work with orthogonal vectors or orthonormal vectors, that is significantly easier. So that is what the Gram-Schmidt process is about. And also, if we can do that, we'll learn another matrix factorization method called a QR factorization. Okay, so just one more section left in the semester. I'll talk to you in that video.